52 years. That is how long it has been since a human being last walked on the moon. Neil Armstrong, Buzz Aldrin, 12 astronauts total. And then, nothing. But what if I told you that the next time we go back, we are not leaving? NASA is not planning another visit. They are planning a permanent base. A nuclear-powered, ice-mining, rocket fuel-producing outpost on the surface of the moon. And the construction has already begun. This is how NASA will build a base on the moon. Before we talk about buildings and reactors, we need to talk about location. Because NASA did not pick their building site randomly. The target is the lunar South Pole. Specifically, a region near a crater called Shackleton. And once you understand why, everything else makes sense. Here is the first thing you need to know about the moon. Its axial tilt is just 1.54 degrees. Compare that to Earth's 23.5 degrees. The moon is almost perfectly upright. And that tiny tilt creates two extraordinary features near the poles. Feature 1. Peaks of eternal light. Because the sun never rises high near the South Pole, it just skims along the crater rims in a permanent low-angle glow. Certain ridges and peaks near Shackleton crater receive sunlight for up to 89% of the entire lunar year. For solar power, that is extraordinary. While the lunar equator cycles through 14 days of blazing sun, followed by 14 days of complete darkness, the South Pole ridges are almost always lit. Feature 2. Permanently shadowed regions. Some crater floors near the South Pole have never seen sunlight. Not in millions of years. Not in billions of years. The temperatures inside these craters drop to negative 250 degrees Celsius, colder than the surface of Pluto. And locked inside that permanent darkness? Water ice. In October of 2009, NASA's LCROSS mission crashed a spent rocket stage into a permanently shadowed crater called Cabeus at 2.5 kilometers per second. The impact threw a plume of debris 10 kilometers into the lunar sky. Scientists analyzed that plume in real time and found water ice making up roughly 5.6% of the excavated material by mass. Later analysis from the Lunar Reconnaissance Orbiter estimated that the moon's permanently shadowed regions may hold up to 600 million metric tons of water ice, concentrated near the poles. 600 million metric tons. Now here is the part that changes everything. On the moon, water is not just water. Split water into hydrogen and oxygen using electricity, and you have liquid rocket fuel. The same propellant that powered the space shuttle main engines. If NASA can produce rocket fuel on the moon stops being a destination and becomes a fueling station. A launch pad for the entire solar system. That is why they chose the South Pole. That is why China is racing to the South Pole. And that is why getting there first matters enormously. Now let's talk about what NASA is up against. Because the moon is not a friendly place to build anything. Challenge 1. Temperature extremes. At the lunar equator, surface temperatures swing from positive 127 degrees Celsius during the day to negative 183 degrees Celsius at night. That is a swing of 310 degrees. And because one lunar day lasts 14 Earth days, every material, every seal, every circuit must survive that cycle, repeatedly, for years. Challenge 2. The dust. Apollo 17 commander Gene Cernan called lunar dust the villain of the entire mission. Unlike Earth soil softened by wind and water, lunar regolith is made of jagged, electrostatically charged particles, averaging 70 micrometers in size, with some submicron grains. They cling to everything. They scratch helmet visors. They clog mechanical joints. They infiltrate electronics. Left unchecked, lunar dust would destroy a base camp within months. Challenge 3. Radiation. The moon has no magnetic field and no atmosphere. Astronauts on the lunar surface receive approximately 380 millisieverts of radiation per year. That is roughly 200 times the average annual dose on Earth. A single large solar particle event could deliver a dangerously high dose in just hours. Every habitat must be shielded. Every EVA is a calculated risk. Challenge 4. Vacuum. The moon's surface pressure is approximately 3 times 10 to the negative 15th power atmospheres, 1 trillion times less than Earth's atmosphere. Every habitat is a pressure vessel. Every airlock is a matter of life and death. Human tissue exposed directly to lunar vacuum survives for seconds. Challenge 5. Isolation. A signal from the moon takes 1.3 seconds to reach Earth. That sounds fast, but if a critical system fails, there is no rescue crew coming. There is no repair technician you can call. Every component must be designed for redundancy, for autonomous operation, and for repair by astronauts in bulky spacesuits 384,400 kilometers from home. These 5 challenges dictate every single design decision in the Basecamp plan. Keep them in mind as we walk through exactly how NASA intends to solve them. NASA's approach is deliberate and incremental. Think of it less like building a house and more like building a city, one district at a time, each mission adding a new layer of capability. Phase 1. Robots go first. No human arrives at an unprepared site. Before any astronaut sets foot on the South Pole, robots scout it, map it, drill into it, and begin setting up infrastructure. NASA's Commercial Lunar Payload Services program is already delivering. In early 2024, Intuitive Machines' IM-1 lander became the first commercial spacecraft to successfully reach the moon. In March 2025, Firefly Aerospace's Blue Ghost mission landed in Mare Crisium and operated for weeks. In early 2025, the IM-2 mission carried a drill designed to penetrate 1 full meter into the regolith near the South Pole to directly sample subsurface ice for the first time in history. Also deploying before crew, the Lunar Terrain Vehicle. NASA contracted 3 companies, Intuitive Machines, Lunar Outpost, and Venturi Astrolab, with bids ranging from $1.69 billion to $1.93 billion, to build a rover that can carry 800 kilograms, travel 20 kilometers without recharging, operate continuously for 8 hours, survive the lunar night, and handle slopes of up to 20 degrees. It operates fully autonomously before a single astronaut arrives. Phase 2. First boots, first habitat. Artemis 4, targeted for early 2028, will be the first crewed lunar landing since Apollo 17 in December 1972. 2 astronauts, 6.5 days on the surface, 2 to 5 spacewalks, all within a 2-kilometer radius of the landing site. But while astronauts are exploring, cargo missions are delivering the foundation surface habitat. This is a fixed structure designed to house up to 4 crew members for stays of up to 30 days. One of the leading designs, called Lunar, developed by AI Space Factory in collaboration with NASA's Kennedy Space Center, is 3D printed using a composite made from lunar regolith. The structure is then buried under 2.7 meters of compacted moon soil. The moon's own dust becomes the radiation shielding. No construction material needs to be shipped from Earth. Joining the habitat, the Habitable Mobility Platform. Think of it as a pressurized RV. Astronauts can live inside it for up to 45 days without returning to base, traveling hundreds of kilometers across the lunar surface in a shirt-sleeve environment. No spacesuit required inside. This single vehicle transforms the exploration radius from 2 kilometers to potentially hundreds. Phase 3. The reactor that changes everything. Solar panels cannot sustain a moon base through 2 weeks of total darkness. Batteries large enough to store power for 14 consecutive days would be catastrophically heavy. The only viable solution is nuclear fission. The White House has directed NASA to deploy a nuclear reactor on the Moon by 2030. Current targets call for a system producing at least 100 kilowatts of electrical power, continuously, day and night, through every lunar cycle, for at least 10 years without refueling. 100 kilowatts powers everything: life support, ice mining operations, rover charging stations, science instruments, communication relays. It is the heartbeat of the entire base. Lockheed Martin's concept uses a Brayton cycle power conversion system, high-efficiency gas turbines that convert nuclear heat into electricity at power levels above 50 kilowatts. The reactor would be surrounded by walls of compacted regolith called berms, which act as radiation shields. Engineers have calculated that proper regolith shielding reduces the required safety exclusion zone from over 2.5 kilometers down to just 90 meters. The Moon builds its own radiation wall. The reactor is designed to operate autonomously for 10 years without a human technician ever touching it. No reactor on Earth has ever been built to those specifications. This is engineering at the absolute edge of what humanity can do. Here is the economic reality of space exploration. Launching mass from Earth to the Moon costs between $800,000 and $1.5 million per kilogram. Every kilogram of water, oxygen, or rocket fuel produced on the Moon directly cuts that cost. At scale, this transforms the base from a money pit into something that begins to pay for itself. The process is called in situ resource utilization, ISRU, and it works like this. Step 1. Robotic mining vehicles collect regolith from permanently shadowed regions where ice concentration is highest. Step 2. The excavated soil is heated. Ice sublimates, turning directly from solid to gas, and is captured in cold collection chambers. Step 3. Using power from the fission reactor, captured water is split by electrolysis into hydrogen and oxygen. The oxygen goes to life support. The hydrogen becomes rocket propellant. Step 4. Both gases are cryogenically stored in insulated tanks for future use. And water is not the only resource. Lunar regolith is approximately 45% oxygen by mass, locked inside metal oxides. NASA already proved this concept works. The MOXIE experiment aboard the Mars Perseverance rover successfully extracted oxygen directly from Martian soil. A scaled-up version is planned for the Moon. The long-term vision? Lunar-produced propellant could reduce the cost of a crewed Mars mission by an estimated 30 to 40%. The Moon is not the final destination. It is the fuel depot that makes every destination beyond it reachable. Now for the part of this story that does not make enough headlines. We are in a second space race, and the stakes are higher than most people realize. China's lunar program has been relentlessly competent. Chang'e 4, first spacecraft to land on the far side of the Moon. January 2019, Chang'e 5 returned 1.731 kilograms of fresh lunar samples to Earth. December 2020, Chang'e 6 returned samples from the lunar far side for the first time in all of human history. 2024, China's announced target for crewed lunar landings, 2030. China and Russia are also jointly developing the International Lunar Research Station, also targeting the South Pole, also targeting the water ice. There are currently no internationally agreed upon rules governing who can extract what from the Moon. The Outer Space Treaty of 1967 prohibits any nation from claiming the Moon as sovereign territory. But it says nothing about resource rights, nothing about who controls access to the ice. The first nation to establish a functioning, water-producing, nuclear-powered base at the South Pole will shape who has access to the Moon's resources for the rest of this century. NASA's Artemis Accords, a set of principles signed by 48 nations as of 2026, establish frameworks for safety zones, resource extraction, and transparency in space exploration. China and Russia have not signed. The Moon is the first contested frontier of the space age, and the construction timeline is not just an engineering challenge, it is a geopolitical one. Let me leave you with this. Every human civilization that has ever existed on this planet has looked up at the same moon. For 300,000 years of human history, it was unreachable. A light in the sky, a myth, a dream. We went there once, 12 people, a total of 80 hours on the surface across 6 missions. And then we stopped. Now we are going back. Not to visit, not to prove a point, but to stay. To drill into ancient ice, to print lunar dust into walls, to split water into rocket fuel, to power a base with a nuclear reactor through 2-week-long nights in one of the most hostile environments in the solar system. By 2028, human beings will stand on the lunar South Pole for the first time in history. By 2030, a nuclear reactor will be running on the surface of the Moon. By 2035, astronauts will spend months at a time in a permanent outpost, 384,000 kilometers from home. And everything they learn, every system they prove, every failure they survive, will become the blueprint for Mars. The Moon will not be empty much longer. If this video gave you that feeling, that electric sense that we are living through something historic, hit the like button and subscribe. Every fact, every number, every mission name in this video is sourced from NASA's official documentation and peer-reviewed science. The next chapter of this story is already being written. I will see you there.